Swayam Prabha. Digital India. Educated India.
Welcome back to the lectures on advanced calculus for engineers, and this is lecture number 16. We will be talking on the Taylor's theorem for multivariable calculus. So, in particular we will go through what is the Taylor's theorem in this case, and there will be some worked problem. So, Taylor's theorem for a function of single variables, just to recall, and that was already discussed in this course. So, assume that the function f has all derivatives up to order n plus 1 in some interval containing the point x is equal to x naught, and then we have written or we have expressed the function in the neighborhood of this x naught point. So, x naught plus h is equal to f x naught, h times the derivative at x naught, then h square by 2 the second order derivative, and so on, and we have the nth order derivative by which was multiplied by h power n over factorial n, and there was a remainder term which was expressed. So, we can continue this like h power n plus 1 factorial n plus 1, and here the n plus 1th derivative at some this unknown point xi, where xi was between this x naught and x naught plus h, or we call this x. So, this x means here x naught plus h. Well, so now we move to the Taylor's theorem of a function of two variables, and in this case the result is that if a function is defined of course in some domain and have continuous partial derivatives. So, now we are talking about the partial derivatives up to n plus 1th order, again in the some neighborhood of this x naught y naught point, and then we can express again this function in the neighborhood of this x naught y naught point by this expression here on the right hand side. So, the function value at x naught y naught, then we have the first order derivative terms. So, h times del f over del x, k times del f over del y, and these derivatives are evaluated at x naught y naught point. Then we have 1 over factorial 2, we have the second order terms which will be evaluated again at x naught y naught point. So, here this operator which we have written, so that will be clarified little later, that how do we get and what is the meaning of this square here at f x naught y naught. But just to clarify that this is like the usual power we have. So, here like h square and the second order derivative. So, it is not del over del x whole square, it is the second order derivative of this f at this x naught y naught point, and then we have mixed term 2 h k, and here the mixed derivative will come del x del y of this f, and again at that x naught y naught point, and then the last term will be the k square term and the second order derivative of f with respect to y and evaluated at x naught y naught point. So, this is the meaning of this square and then the cube term and so on. So, this will go up to this 1 over factorial n, and here we have again this power n, the meaning which is clarified just for the square term will continue, and then we have the remainder term here, which remainder is again similar to what we have discussed before, 1 over factorial n plus 1 and then we will continue this order n plus 1, and instead of that fixed point, now we have a variable point, or rather unknown point here, which where the argument lies between this x naught to x naught plus h, and the second one from y naught to y naught plus k, which is expressed in terms of the theta here. Theta varies from 0 to 1. Well, so the Taylor's theorem for functions of two variable, we will go through that how to get the result we have just discussed before. So, for simplicity, we restrict here this discussion for n is equal to 2, that means we will go the terms up to order 3. So, let x is equal to x naught plus th and y is equal to y naught plus tk, where this t is some parameter between 0 and 1, close interval 0 and 1, and we define this function phi t as x naught plus th and y naught plus tk. So, f is a function of, basically f is a function of x and y, and where this x is equal to x naught plus th and this y is equal to y naught plus th. So, at the end this is a composite function of t, the f is a composite function of t, since this f is a function of x and y, and x is a function of t and y is a function of t. So, we know the formula how to get the derivative, that means how to get this phi prime t. So, directly this phi prime t using that chain rule which we have discussed in the previous lecture. So, that will be del f over del x and dx over dt, del f over del y and dy over dt, that chain rule. So, this del f over del x and dx over dt. So, dx over dt will be just h. So, that will be the h term, and del over del x will remain as it is, and from here dy over dt, because y is y naught plus tk, we will get this k term, and we have the partial derivative with respect to y of f at that point here x comma y. Well, if we continue further, because at the end we will apply the Taylor's theorem for single variable. So, we will apply the Taylor's result on this function phi t, and t is just the single variable there. So, there we need these derivatives. So, we need phi prime t, we need phi double prime t. So, to get the next order derivative, so what we have here, we have this h and we have del f over del x, and then we have k and del f over del y, and then we go for the higher derivative. So, this was phi prime t, and just to get now phi double prime t, we have to now differentiate here, we have to differentiate here, and we have to use that chain rule again. So, basically this h as it is, and then we have to use the chain rule. So, del f over del, so the double derivative with respect to x square, because we have to differentiate with respect to x as it was there, and one h will come because of this dx over dt. Then we will have del 2f over like del y, and so del y del x, and the k will also come as it was there before. So, this is the result from the first term. Similarly, from the second term also we will get, we have del f over del y, and then we will differentiate again, we have to use that chain rule. So, for the del f over del y, first we will differentiate with respect to x, that means del 2f over del x del y, and dx over dt, that is h, and then again del 2f over del y square and dy over dt, that will be the k. So, we have again used the chain rule here and chain rule there, and as a result what we will get with this h, we will get the second order derivative into h, second order mixed derivative into k, then we will have k there, then this mixed order derivative with h, and the second order derivative with respect to y, and then k. So, this is in each term here the chain rule is applied, and here also the chain rule is applied. So, from the first we are getting this, and from the second we are getting these terms. Well, which we can put all together. So, we have h square, the second order derivative term, we have a mixed term here with hk, here also we have hk, that means 2 hk and this del 2 f over del x del y, We have also here the k square term and del 2f over del y square. So, this term h square del 2f over del x square 2hk and this mixed derivative k square and this derivative, this is what we have written in this form, h partial derivative with respect to x plus k partial derivative with respect to y whole square. So, this is a kind of notation we are using for simplicity, because this is easy to write and also easy to understand. Also, it is very easy to relate to the Taylor's theorem of one variable. So, these are the second order derivatives. Now, if we go for the third order derivative of t, so again for each of those terms we have to apply the Taylor's we have to apply that chain rule. So, for the first term, for the second term, for the third term, applying the same chain rule, we will get these terms, and once we simplify this, we will get h cube, we will get 3h square k, the third order term 3hk square. So, h means only partial derivative with x will come, k square means here y square will also come, and so on. So, these third order derivative terms we have written then in the cubic form. So, h del over del x plus k del over del y power 3. So, we have this third order derivative, first order, second order, all these derivatives of phi we have. Now, we can use the Taylor's theorem on this function phi t. Phi is a function of one variable. We know the result for a one variable and we will express around that point 0. So, phi t is phi 0 plus t phi prime 0 t square by factorial 2 phi double derivative at 0 t 3 factorial 3 double derivative at theta t, and theta is between 0 and 1. So, basically this argument will be between 0 and t, which is the last term or the so called that remainder term we have here for this n is equal to 2 case. So, this phi at 1, if we compute phi at 1, what will be that? Phi 0, phi prime 0 and so on, and t we have just replaced by 1. So, if this is true for any t there, so we just putting this t is equal to 1 for some reason, because phi was this x 0 plus t h and this y 0 plus t k, and the t 1 means we have x 0 plus h and y 0 plus k, which will be the Taylor's theorem for two variables. So, having this relation now on phi 1, we have the phi t, we have the phi prime t, we have computed phi double derivative, we have computed phi the triple derivative, and we have also this relation that phi 1 is equal to phi 0 and so on phi double prime theta. Now, we can substitute in this relation. So, what will be phi 1? So, phi 1 will be f x 0 plus h and y 0 plus k. From here t will be just 1. Now, this phi 0, so phi 0 will be f 0 y 0. Now, the double derivative at 0, so first derivative. So, this is the first derivative, and when t is 0, so t 0 means this term will not be there. So, this will be like f at x naught y naught. Similarly, the second order derivative at x naught y naught and so on, and this is precisely the Taylor's theorem for two variables, because here we have f x 0 plus h y naught plus k. This is a point in the neighborhood of this x naught y naught, because h and k can take any value. So, this will be a point in the neighborhood of this x naught y naught, which we can write down in terms of f x naught y naught, the first order derivatives, the second order derivatives, and then at the end this is the remainder term which we have. So, the first part will be the Taylor's polynomial, as a whole result it is called Taylor's theorem, and this last one it is called remainder term. So, we can extend this idea. This was just for n is equal to 2, but if we extend this, we will get for any n. So, this is f in the neighborhood of x naught y naught. We have the constant term. So, f x naught y naught, the first order term, the second order term, and so on. The nth order term will continue, and then we have this remainder term where n plus 1 and n plus 1 other derivative on this unknown point will come, x 0 plus theta h, y 0 plus theta k. So, this first argument will be from x naught to x naught plus h. this belongs to this interval, and the second one this will belong to again y naught to y naught plus k, y naught to y naught plus k, which we have just defined here using this theta, because that is those xi1 or xi points rather, or xi1 xi2 points. So, they belongs to exactly the variation what we have here, somewhere in between x naught to x naught plus h and y naught to y naught plus k. So, the structure is absolutely the same as we have in case of one variable. The only difference is that there we used to have only one ordinary derivative. So, but here also we have the first order derivative, there also we had the first order derivative, here we have all the second order derivatives terms, including those mixed and all, here then third derivative, fourth derivative and so on. So, structure remains the same as we have in case of one variable calculus. Alternatively, this can be also written if we want to have like f x y is equal to, we want to express in the x naught y naught point. So, f x y is equal to f x naught y naught plus, then instead of this h, the difference of this will come x minus x naught, y minus y naught, x minus x naught, y minus y naught and so on. So, everywhere the h here basically is x minus x naught and y is k is y minus y naught. So, that is the only difference in this and in this form of the Taylor's theorem we have. Coming to the problem, so we will be doing calculating the Taylor's approximation or theorem, we will be applying to some functions. So, here find the quadratic polynomial approximation to the function f x y is x minus y over x plus y about this point 1 comma 1. Point is given, the function is given, and we are talking about the quadratic polynomial approximation. So, we will go up to the second order terms. That means, we need to get the f x, the partial derivative of f with respect to x, that of course, we can get directly by that quotient rule. So, here the square and then we have the derivative of this, that is 1, and this term x plus y minus the other term and the derivative of this. So, we will get here 2 y over x plus y whole square, and f x at 1 point. So, if we get at 1 comma 1 point, the value will be, so just 2 over 1 comma 1, so 2 4, so this is half. So, we will have here the value half, and f y x comma y we have again from the same expression using that quotient rule for the derivative, we can get this second order derivative, and at the value 1 1. So, we will substitute here 1 1, we will get the value minus half for this derivative. As discussed, we have to go for the quadratic polynomial. So, we need to get the second order derivatives term. So, f x x, so that means we will differentiate that again once more. So, this term will be differentiated once again with respect to x. As a result, we will get this minus 4 y and x plus y cube, and then if we calculate this derivative at that point 1 comma 1, we will get the value minus half. Similarly, the double derivative of f with respect to y, we will compute from here, we will get 4 x over x plus y power 3, and again at 1 1 if we compute, the value will be half, and there will be a mixed term. So, f x y, so either we can get this from this one by differentiating this with respect to x, or by differentiating this with respect to y, we will get this f x y, because f x y and f y x will be the same for such a nice function. So, there should not be any problem, and again at 1 comma 1 we will get this, and the value will be just 0. Okay. So, having this, now we have f x at 1 1, the value is half, f y at 1 1, the value is minus half, f x x is minus half, f y y is half, and this mixed order derivative was 0. So, we have all desired first and second order derivatives, which we can now substitute here in the polynomial. So, p 2 x y will be f 1 comma 1, as per the our expansion, we will have here f x 1 1 x minus 1, f y 1 1 y minus 1, f x x 1 1 x minus 1 whole square, and so on, all other terms there. We can continue with this, and then we will substitute. So, there will be 2 terms of the first order here, and of course, 3 terms will be for the second order derivative, whereas this is 0 because of this one. So, this term will not be there, this we can put it 0. So, what we will get, this was half there, f 1 1 was half. So, there should be a term half here which is missing. So, f 1 1 was 0. So, f 1 1 was 0. So, there will be no term, and then we have this f x 1 1, this is half. So, x minus 1, then we have f y 1 which is here minus half with y minus 1, then we have f x 1 comma 1 which is minus half, and half is already there. So, minus 1 by 4 the square term, and we have here this half and half 1 by 4, and then y minus 1 whole square. So, this is the Taylor's polynomial of degree 2, which we have computed using this first order and the second order derivatives, and applying this Taylor's formula to get this Taylor's polynomial of basically degree order 2. So, here we have this function f x y, x square plus x y, and then we have y square. So, be linearly approximated. So, only the order 1 terms linearly approximated by the Taylor's polynomial about this point, that is the one part, and find out the maximum error in this approximation at a point in this square. So, we are talking about that square. So, x is equal to 1 and y is equal to 1, and then we have a square there with radius this point 1. So, around this square or around this 0.11 there is a square here, where we are saying that what would be the maximum error of this approximation if we approximate this by the linear polynomial, the linear Taylor's polynomial, then what will be the maximum error if we take any point in this square. See, the polynomial will be the Taylor's theorem we will be using around 1 comma 1. So, here the question is, if we take any point from this square, what could be the maximum error. So, here we will use the remainder term to get this maximum bound on the error. So, for that we need the f x. From here we can easily get f x will be 2 x plus y. We can get f y also, we can get f x x as well, and f y y as well, and then the this f x y, the mixed derivative. So, either from here, so if we differentiate with respect to y, we will get 1, or here we differentiate with respect to x, so we will get 1 again. So, that is the value 1. And now, remember the remainder term. So, we will make use of the remainder term here, because that is basically the error. So, we have the Taylor's polynomial, and then here the Taylor's polynomial plus this remainder term. So, the question was, if we approximate our function f by this linear term, then what will be the maximum error. So, the maximum error means this remainder is the error, and we will approximate that from the remainder term. So, the remainder is half and x minus 1 the first derivative, y minus 1 the del o del y, and these all are basically the second order terms, because the first order terms are already used in the linear approximation or the Taylor's polynomial. So, here these are the second order term 1 over factorial 2, which is just 2, and x minus 1 this second order derivative plus y minus 1 second order derivative with respect to y, and the product term will be with the mixed order derivative, and then f will be evaluated at this 1 theta x minus 1 and 1 plus theta y minus 1. Well, so this is x minus 1 whole square, this is value is 2 there, the product term here it is value 1, the square term, and there is a value 2 again as per our calculation. So, if we substitute those, we will get r 1 x minus 1 whole square, the product term, and y minus whole square, and these are basically the constant. The second order terms were just the constant. So, it does not come into the picture, this theta and all. So, this variable point is not there because of these constant values. If they depend on x and y, of course, this theta will also come here. So, here things are much easier. So, we have also the square where we want to pick those x and y and see what is the error between that linear polynomial and the actual function. So, that is x minus 1 is bounded by 0.1, y minus 1 is also bounded by 0.1. So, this r 1 we will compute within this square. So, the maximum error we can get here, that is x minus 1, the maximum value can be 0.1. Here also we know the maximum value, that is 0.1, 0.1, and here also we know the maximum value 0.1 square. So, we have looked for what is the maximum value of this r 1 in the given square, and that is coming out to be 0.003. So, what we conclude from here, that when we approximate this given quadratic term x square plus xy plus y square by the linear term of this Taylor's approximation, in that case the maximum error between this linear approximation and the given function can be 0.03, and we can choose this x and y from anywhere around this 1, 1 point from this square region, which is bounded by this 0.1 and 0.1. Well, so this is the last problem. Obtain Taylor's formula about this 0.00 involving derivatives up to third order for the function cos x plus y. So, now we will again get the Taylor's formula which involves the derivatives up to third order. So, we need to get, of course, the Taylor's theorem now, f x y, f 0 0, the first order terms, the second order terms, and then the third order terms. But then since we are talking about the Taylor's formula, not the Taylor's polynomial, so we have to have that remainder term which will include these third order derivatives. Well, so for that we need the first order derivatives, the second order derivatives, and third order derivatives. So, first and second order derivatives at 0 0 and third order derivative we need at the general point. So, the function is given f x y as cos x plus y. So, it is easy to get all these partial derivatives. F 0 0 will be just 1, and the first order derivative f x will be minus sine of x plus y. And if we get this first order derivative at 0 comma 0, because of the sign we will get that 0. F y will be again minus sine x plus y, and this value will be also 0. So, the first order terms, these terms will vanish actually because of this first order derivative is 0. The second order derivatives f x x, f y y, or f x y, whichever you get, it will be cos x plus y, and at 0 0. So, all of them will be just minus 1. So, we have the first order derivatives which are 0. So, this term will vanish, and here all these second order terms, whatever we will get here, the x square, then we will get 2 x y, and then we will get y square, and together with this minus 1 will be coming because the second order derivatives we have minus 1. So, this term is also clear. Now, for the third order terms we have to compute the derivative at x y and then at theta x and theta y. Well, so here we have the third order derivatives, and in this case, so we compute. So, f x, the all triple derivatives here, the mixed order and the third order with respect to y, third order with respect to x, that will be, because we have the cos there, it will become just the sine x plus y. So, all the third order derivatives which will appear there, we will have just sine x plus y for all. Okay. So, f x x theta y, because this is required there, we will get theta x and theta y for x and y for all mixed order derivatives which will appear in the third term. So, we have f x y is equal to f 0 0 was 1 and we have no first order terms because that will be cancelled out, and we will have minus this 1 by factorial 2 because that value was minus 1 for all those derivatives. So, we have x square 2 x y plus y square, and then we have 1 over factorial 3 and these third order terms, because here the value was 1. So, there is no change, but only x cube 3 x square y 3 x y square, and this so this is the last term here where we have the remainder basically, and in that case the derivative is sin x plus y. So, that means sin theta x plus theta y when we evaluate at theta x plus theta y, and since it is same for all these terms, so we can take that common there, and what we will get x cube, and we will get 3 x square y 3 x y square and then y cube as a result of this, because when we open this is 1 over factorial 3 and we have x cube and we will get f x x x, and then we will have here 3 x square y and there will be term x x and y, there will be a term 3 x y square and corresponding this derivative, and we will have also y cube there and we will have f y y y. So, all these derivatives are constant in the are same in this case, and the value is this sin theta x plus theta y. So, therefore, we have taken that out, sin theta x plus theta y, and then what is with us here now, x cube, then we have 3 x square y, we have 3 x y square, and then we have y cube as a result. So, this is the first order term, second order term, and then we have the third order term as remainder. So, this f x y can be written as 1 minus this minus half x plus y whole square 1 by 3, this is x plus y whole cube and sin theta x plus theta y. So, this is the Taylor's theorem. Yeah, we are not talking about here the Taylor's polynomial. If we say Taylor polynomial of order 2, this is the Taylor's polynomial of order 2 or order 3 if you want to get. So, we have to then evaluate that also at 0 0, but in this case it will be 0. So, there will be no second order term, there will be fourth order term next to this one. So, there is a difference. If we call Taylor's this polynomial, then we pick only those terms except remainder, but as a Taylor's theorem then we have to also write the remainder term. Well, so this is all about the Taylor's theorem of functions of two variables. So, just to conclude, we have learned the Taylor's theorem for functions of two variables, and this idea can be also generalized for the functions of three variables. So, here that was the point in the neighborhood which can be expressed in terms of this x naught, the first derivative of the function at that x naught y naught, the second order derivative of the function at x naught and y naught, and so on up to nth order, and there will be a remainder term where we have to evaluate that n plus 1th order terms at some variable point or unknown point which will lie between this x and x naught plus h and y naught plus k. So, the structure of this Taylor's theorem for functions of two variable remains the same as the case of a function of one variable, but of course, here the more these partial derivatives are coming into the picture. Well, so here are the references which are used for preparing this lecture, and with this I thank you for your attention. Thank you very much.